Alright, so if you see the first slide says, have you had enough Howie yet? It's only been about 12 weeks. Well, guess what? You have the whole year with me, so bear with me. Anyways, we're on to yet another unit. And yes, it has to do with heat. So go figure. Last week we talked about thermodynamics. This week is about heat transfer. It's very important. We've been talking a lot about it. When we talk about energy conversions, which I feel like we've been talking about for about 2 weeks now, when we talk about that, we always talk about the transfer of heat and how heat is lost to the environment. So let's talk a little bit more about that in depth. So heat is always in motion, moving from one place to another, whether it's from our bodies to the atmosphere, from some kind of contraption like some mechanical device to the atmosphere to the ground, you name it. It's always in motion. It's always moving from one place to another. I always love these pictures when you can see the heat and the heat waves rising off of the concrete or wherever it might be. It's very cool. But heat is a type of energy, and so obviously when we look at it through the atmosphere, it can distort things. That's why we see the little wavy lines. But before we get in, I've got to show you guys, share with you actually, not necessarily show you, but I am going to show you a video. Some wise words from one of my favorite guys. If I would have done things different, maybe I would have tried to be a little bit like Bill Nye. So watch this, and then we'll come back and discuss more.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill, 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 Bill. Bill Nye the Science Guy. The mountains are icy, but they've got motion of molecules. Ha! See, even cold things have heat. Things like snow and icy mountain lakes and glaciers. They've got heat. Anything with molecules has heat. It's just that the molecules in cold things are moving more slowly than the molecules in warm things. You with me? Okay, y'all ready? Sing along. It doesn't matter whether something feels cold or hot. If molecules are moving, it's something all things got. You know the words now, sing along. It doesn't matter whether something feels cold or hot. Here's a question. Which has more heat energy? This hot burning match or this beautiful ice sculpture of science? Well, the match is hot, right? The sculpture's cold. Well, they're both made of molecules, right? But which has more molecules? Well, the ice sculpture. A lot more molecules. So although they're much colder than the match, they actually have more heat energy. More molecules, more heat energy. Think of it this way. Suppose you tried to take a burning match and use it to melt the whole ice sculpture. Well, it's not going to happen, right? I mean, the match is going to run out of molecules long before the sculpture. So, more molecules, more heat energy. Ooh, ow, ow. Careful. He broke the swan. Bill Nye the Science Guy.
Okay, so who doesn't like Bill Nye? I mean, I think Bill Nye is pretty entertaining, even though he's very quirky and kind of cheesy. But wait a minute, so am I. So I wanted to show you guys that clip because it's very important to understand the basics of heat. Okay, so the basics of heat are that, just like Bill Nye had said, everything has heat. Okay, if I pick up my phone or this marker here, all the random things next to me, they all have heat. But depending on how fast the molecules are moving determines how hot they are. Okay, so think about this. Let's take water. So you have water in the frozen solid state of ice, right? The molecules are very slow moving. That's why it's a solid, because they're basically they're so tight together and they're not moving very fast, so it becomes a solid, okay? But then as you add heat to it, all of a sudden it starts to melt and it becomes a liquid, and those molecules are moving a little bit faster. Now obviously it's not hot water necessarily, but it's a liquid. Liquid meaning there's more energy and typically more heat, so that those molecules are moving faster. And then all of a sudden you put that water in a pot and you boil it, And those molecules are moving so fast that some of them fly away as water vapor in the form of gas. So gas has the highest energy and typically the highest heat amount, okay? So think about the way that molecules move. How fast they're moving is also going to determine how much heat. And like Bill Nye had said, the larger mass, there's going to be more molecules. So typically there's going to be more heat energy regardless of the actual temperature of that thing. Okay, so there's just some basics. Now let's talk about the three ways that heat moves. We have one that is called convection. Convection is the heat transfer through liquid or gas. So many of you guys have heard of a convection oven. A convection oven uses the heat that transfers all around through air so that it's typically a better way to cook things as opposed to your conventional oven, okay? But a convection oven kind of circulates that heat and cooks things nice and, very well rounded, okay? But also you have convection heat through this in a, actually this is talking about the three different types in this picture right here, but convection is heating this liquid, okay? Now conduction, we'll talk about in just a moment, is going to heat, like say the handle or even the pot, and then we'll talk about radiation. Okay, so convection is heat transfer through a liquid or gas. That can also mean air. Okay, so anytime that the air is warming, whatever it might be, the ground or the greenhouse effect in your car. So in the wintertime when you get in your car and even though it's freezing outside and your car's nice and warm, that's the greenhouse effect. Okay, that heat actually gets trapped in. But there's convection because that heat is coming through air and it actually penetrates through that glass, but it can't escape. So that's why your car is nice and toasty in the wintertime if it's parked in the sun. Okay, so conduction, the heat transfer through a solid. So like we talked about here, conduction is going to take that heat and it's going to transfer it to a solid. And we've talked about before that there are great conductors, okay? A conductor is a type of material that can conduct heat. It can take heat and transfer it elsewhere. Okay, is rubber a good conductor? Not so much. Rubber is not going to hold heat, but you have some kind of metal. That's why they typically don't make pots with metal handles, because the conduction is going to take this heat from this fire, okay, or your stove, and it's going to heat that metal, handle, and you won't be able to pick it up. So typically they're plastic or rubber or some kind of material that's not a good conductor, okay? But obviously, when you heat a pot full of water, that pot is the first thing to heat up. It's a great conductor, okay? And then it's going to start working through to, whatever that substance is inside, okay? That's conduction. So convection, transfer through a liquid or gas. Conduction, heat transfer through a solid using some kind of a conductor. Okay, there are many different types of conductors. Some are better than others. Most of them happen to be metals. All right, and the last thing is radiation. Radiation is heat transfer from a light source. So say, for instance, a fire, a nice campfire. You're warm in your hands. You're getting ready to toast your little s'mores, right? That is radiation. You're feeling the heat from a light source, okay? So that's all that is. Three ways that heat is transferred. Remember them. Convection, conduction, and radiation, okay? All pictured in this one picture, so put that in your memory. All right, now, reactions with heat. And when we talk about this in the Class Connect, I'm going to give you guys some visuals on these, more so than just a picture. But when we talk about an exothermic reaction, we talk about a chemical reaction that releases heat. So I love this picture of the lovely fireworks, okay, because we love fireworks, especially on the 4th of July and New Year's and so forth. And when we see that, we're seeing an exothermic reaction. That basically, it's going to release heat and energy. So it starts off from a lower energy, okay? So that firework starts off with a low energy. You add a little heat to it, you light it, and a huge, huge reaction occurs, okay, with lots of heat and lots of energy. So when you end up with more energy, you start off with little, end up with a lot, that's an exothermic reaction. Kind of heat is exiting out. Energy is exiting out of that reaction, okay? On the other hand, we have an endothermic reaction where reactions are going to absorb energy, such like photosynthesis, where you have this endothermic reaction. It's going to take energy from the sun and it's going to absorb it, and you end up with less energy, less heat than what you started off with, okay? So there are many different examples. You're going to see some of those in class, and hopefully then you'll be able to describe what it is that we're talking about. Endothermic reactions, exothermic reactions, what do those mean? Okay, endothermic, you start off with a great more deal of energy or heat, and you, after that reaction, you end up with a lot less, so it's going to absorb that energy. Okay, make sure you guys understand all of those concepts. You're going to see those in your unit, so make sure you guys are reading through that, taking notes. Okay, all right, specific heat. This is the amount of energy needed to increase 1 gram of that substance 1 degree Celsius. Every single substance in this entire universe has a particular specific heat. Okay, paper, whatever, you name it. Okay, when we talk about specific heat, we talk about, typically we compare it to water. Water is a very easy thing to compare to, but water has a very high specific heat, meaning it takes a lot more energy to heat up water than it does, say, a good conductor like metal. So that's why you'll see on a cold day the steam rising from a lake, because the heat is actually held a lot better in water because it has a higher specific heat. So specific heat is the amount of energy that is needed to increase 1 gram of that substance, whatever that substance is, 1 degree Celsius. Okay, that's called the specific heat. And that plays a lot into different chemical reactions, how they react, how they hold heat, and so forth. Okay? All right, now what affects the specific heat? There are a couple things that affect the specific heat. Okay? The first thing that's going to affect the specific heat of a particular substance is going to be the structure of the molecule. Molecules that are more complex generally are going to have a higher specific heat. So if you have just a simple molecule of, say, oxygen or, O2, which is the breathable oxygen, blah, 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 breathable oxygen that we use, okay, that's a very simple molecule. And think about how quickly you can heat that. When you blow into your hand when it's really cold and you're like, in the wintertime, or if you just want to play Darth Vader, okay, that air is heated very quickly. Okay, it's a very simple structure, so therefore it's heated quickly. It's going to have a lower specific heat. But the more complex a molecule is, it's going to have a higher specific heat. It's going to take more energy to heat that substance, and that substance is actually going to retain that heat more as well. Also, whether or not it has hydrogen bonds. Hydrogen bonds are found in polar molecules like water. Okay, remember I told you water has a pretty high specific heat, so it takes a lot of energy to heat that water, but also it's going to maintain that water more, or maintain that heat more. So anything that has a hydrogen bond, such as water, has these polar molecules. They're very strong, and they require more heat energy to actually break it. So that's going to raise the specific heat. So when you think about that, you have this hydrogen bond, and it takes a lot of energy to actually break it, as opposed to these, covalent bonds, okay, that are in between some of the molecules. So the hydrogen bonds, a lot stronger, harder to break, going to take more energy. Therefore, you have a higher specific heat, okay? Now, density also affects specific heat, okay? The more dense a material is, the higher specific heat. So denser materials, such as this one right here, where you have more molecules means more density, okay? More density means it's going to take more energy to break that apart and actually, raise the temperature of that, okay? So the less dense something is, again, take for instance air, oxygen, O2. It is not a dense substance, so it does not take much to heat it up. But then you say something else made of, a real dense material, whether that's iron or steel, even though it will heat up, kind of quickly because it's a conductor, it still takes a lot more heat energy to heat it up because it's so dense in comparison to something like oxygen. Okay, so density plays a huge part in that. All right, so an abrupt ending, but I want you guys to take that information and think about it. Again, I want you guys to really use this information and take it to your personal lives. As you look around and you go your day-to-day lives, think about how heat is transferred. Think about all the different methods that you're using for conduction and convection and radiation, okay? Many different things in your lives. If any of you guys live on a ranch and you brand, think about the radiation involved and the conduction involved with just the branding. I think of that because I love to help my friend go brand, and it's really kind of cool. But anyways, nonetheless, think about it in your own lives, how many ways that you can see heat being transferred on a daily basis, okay? So take that. We are going to talk a little bit more about that in class, so we'll see you then.